afternoon, all. Welcome to Samvaad. Today we are continuing with our theme on medical AI. This is in fact the fourth talk on this series. And today we have with us Dr. Raji Mathew. She's a postdoc at IISc-Bangalore, which also happens to be my alma mater. Professor Neelam Sinha is the session chair for today's talk. Professor Neelam is currently an associate professor here at IIIT-Bangalore. Being an expert in the medical imaging and signal processing field, she also is our theme coordinator for this ongoing medical AI talk series. So without any further delay, let me hand over the stage to Professor Neelam. Over to you, Neelam.
Thanks, Nikhil. Hello all. So our next talk on the theme of medical AI is titled Compressed Sensing MRI, Case-Based Sampling to Reconstruction. This is by Dr. Raji Susan Mathew. Now to introduce her, she is a C.V. Raman postdoctoral fellow in the medical imaging group of Department of Computational and Data Sciences in IISc-Bangalore. She obtained a PhD degree in the area of MR reconstruction from Indian Institute of Information Technology and Management, Kerala. Prior to this, she received bachelor's degree in ECE from the Mahatma Gandhi University, Kottayam, and master's degree in signal processing from Cochin University of Science and Technology, Kochi, in 2011 and 13. Her research interests lie in the field of medical image processing, medical signal processing, and reconstruction using deep learning and classical techniques. So looking forward to the talk. So if you have any questions, please feel free to interrupt when the talk is going on. But if you so wish, please post them at the end of it. So you can either use the chat or unmute and ask it yourself. So over to you, Raji.
Today I'll be talking on compressed sensing MRI case-based sampling to reconstruction. So I'd like to acknowledge my current research group, Medical Imaging Group at IISc-Bangalore, and my previous group, Medical Image Computing and Signal Processing Lab at Indian Institute of Information Technology and Management, Kerala. So today's talk includes magnetic resonance imaging and case-based trajectory, Cartesian sampling, MR image reconstruction, compressed sensing, non-Cartesian sampling, some of the state-of-the-art trajectory design techniques, challenges in the design of trajectories, compressed sensing reconstruction, parameter optimization for reconstruction, and an overall summary. So coming to the medical imaging of human internal organs is very important for the diagnosis, treatment, and follow-up. So in this case, MRI is a non-invasive medical imaging technique which is used for visualization of internal organs. And it produces high resolution images with excellent contrast, and it does not have any ionizing radiation. So if we look at the applications, MRI imaging applications, it images over almost all parts of the internal human organs, starting from brain, heart, spinal cord, liver, and knee, as well as different other parts of the human body. Also, we can image using, achieve a qualitative image or a quantitative image using MRI. Also, we can identify the different diseases using MRI, like we can identify stroke, cerebrospinal disorders, neurological disorders, different cancerous tissues, identifying the stages of cancer, and so on. So how data is acquired in the magnetic resonance imaging. So we know that in MRI, there is a MRI scanner, and it has a main magnetic field which is always on. And in the human body, most of the weight, that is 2/3 of the human weight, is contributed by water, and the protons inside this hydrogen atoms in the water molecule contribute to the MR imaging signals. That is actually acquired, that means there are spins inside the hydrogen atoms, and these spins align with the main magnetic field when the body is placed in the main magnetic field. So some certain RF pulses are applied, and when it goes out of this alignment, we remove this RF pulses, and this signal decay happens during this realignment procedure, and that signal is used for MR imaging. So this is the overall summary how the data is acquired inside the MR scanner. So this process happens many times. That means it is repeated many times in order to acquire a particular region of interest in the human body. So coming to the entire routine, that means when an object is placed in the scanner, we scans the particular region of interest and we obtain the signals in the Fourier domain called K-space. So if we say the Fourier domain, we know that most of the energy lies at the center of the Fourier domain, that is center of the K-space, and the signal decay towards the periphery of the K-space. So K-space is not acquired in a single stretch. Multiple pulses or multiple RF sequences are applied in order to acquire the entire K-space region. So it is actually a time-consuming procedure, many number of times to acquire entire. So if we look at the K-space, we can see that this K-space trajectory, in a Cartesian way, if we acquire the K-space trajectory, we acquire line by line, and each line requires a set of pulses. The acquisition of each line of data requires a set of pulses, and this each line acquisition is called a shot, and each shot requires a set of pulses, and that is a time-consuming procedure. So if we want to acquire the entire K-space data, we have to repeat the pulse, applying the pulses for a number of times. That means according to the size of the data, size of the K-space grid we are considering. So the K-space trajectory is usually composed of several segments, which is represented by K of t, and it can be represented as an integral function of the gradients of the magnetic field. So again, here we can see that the Kx direction is typically called frequency encoding direction, and the Ky direction is typically called phase encoding direction. And coming to the Cartesian imaging, if we want to image a particular line in the K-space, some pulse sequences need to be applied. So this pulse sequence means the set of RF pulses and the gradient pulses we need to apply in order to acquire a particular line in the K-space. So the one set of such a sequence is shown here. We have to repeat it equal to the number of lines in the K-space. That means the number of pixels along the Y direction. Here we can see that it starts from, we initially starts with an RF pulse. So it is just to excite the magnetization, and then we apply a GX pulse, then it moves along this arrow 1, and the position comes up to the plus KX max. That means the other end of the X direction. Then what happens? Then we apply another RF pulse shown as 2 in this pulse sequence. So on this application, the position comes to the negative direction, that is minus KX max. Then we apply GY pulse, and with the amplitude of the GY pulse determines how far it comes down in the down direction. If it is negative, it comes down, and if it is positive, it goes towards the opposite direction. So in the next step, then we apply a GX pulse to acquire the entire line of K-space here, as shown here using arrow 4. So this process we have to repeat how many times? If we want to acquire the entire K-space data, we have to repeat it n by times. That is the number of pixels along the Y direction. So this is actually a very time-consuming process. And if we consider the number of this one such procedure or one such application of pulses is called a shot, and then while considering the MR hardware, we have to reduce the number of shots in the undersampled acquisition. So our aim is to how we can acquire the samples with a reduced number of shots rather than simply skipping some points in the K-space in a hardware point of view. So again, if we look at the K-space, we can see that most of the energy is contributed by the center of the K-space. And if we take the inverse Fourier transform, we will get the full image. But if we take only the low frequency part, we can see that we lose all the high frequency information and only the contrast is maintained. So on the other hand, if we remove all the low frequency part with only the high frequency part retained, then we will get only the edges. So in the MR data acquisition, and each frequency point corresponds to all values in the image domain, contribute to all values in the image domain. So coming to the undersampling is that we are acquiring only a subset of samples rather than acquiring the entire case-based data. So coming to the undersampling, if we are leaving out every one line in the case space in between two fully acquired lines, then that is called an undersampling of 2, and that is represented by R is equal to 2. So here we are leaving out every one line in between two fully acquired lines in the case space. So when R is equal to 2, we can see some visible artifacts in the image are shown here, and we can see some 2 artifacts appearing in the image. And similarly, if we perform undersampling of equal to 3, we can see some more artifacts are appearing. And if we again increase the undersampling factor, it will again start increasing. So how we obtain this image is like we undersample the data, that is the case space data, then we zero fill the case space and we take the inverse Fourier transform of the corresponding zero filled case space. So this clearly indicates that we cannot directly take an inverse of the undersampled data to obtain a good quality image or an image similar to the fully sampled image. So we need to perform some extra or additional steps in order, or some algorithmic steps to recover the image of clinical quality. So that is the MR image reconstruction problem. We have the object of interest. We have this scanning protocol where we scan only a limited number of case space samples, and we have to reconstruct the image of the clinical quality from the limited number of case space samples or undersampled case space samples which is available to us. So this procedure or this process is an inverse problem, and that is called MR image reconstruction problem. And to recover an image of good quality, we need to use some special mathematical techniques or some special algorithms to recover a good quality image. So in this case, we use some prior information. The prior information can be either acquiring data from multiple channels, or we can use some prior information like sparsity, low rank, etc. And with that, this is used as a prior information in order to recover an image of good quality. So coming to the MR image reconstruction approaches, conventionally there are 2 types of approaches, that is parallel imaging methods and compressed sensing methods. In parallel imaging methods, we use multiple receiver channels around the object of interest to receive data from. We receive data in all the channels, and we use this multi-channel data to recover our final region of interest or our final image of interest. So again, we have another type of method called compressed sensing methods, where we utilize the fact that the image in that domain itself or in some transform domain, it is sparse, and this sparsity is utilized to recover an image of good quality. So coming to the parallel imaging techniques, these are the conventionally used techniques in magnetic resonance imaging. That these can be broadly classified as image domain methods or case space methods. So whatever case space we have obtained using the undersampling, we can take the inverse Fourier transform, that is, we can directly go to the image domain first, and then we can perform some algorithmic steps to recover the final image. So such methods are called image domain methods. So we are performing the algorithm in the image domain. And this image domain method, the most important method is the sensitivity encoding or sense. So here we require multiple channel data. That is, we are acquiring data using multiple channels. And if we want to undersampling by a factor of 2, at least 2 number of channels are required in this case. So again, the point to be noted is that we are finally we are achieving only a single image in the case of image domain methods. Whereas in the case of case-based methods like grappa, what happens is that we are directly filling the case space first. That means all the missing points which we are not really acquired, we are filling it first. And finally, we obtain all the different filled case spaces of all the channels. And then we take the inverse Fourier transform to obtain the image domain of all that corresponding channels. And that image domain data we will combine to obtain. If we can use different combination methods, we can either use a sum of squares approach, or we can use a complex sum based on whether we have to get a magnitude image or complex image as output. Again, in the case of case space methods, we have some fully acquired samples in the middle of the case space that is called auto-calibrating signals. And that is why these methods are also called auto-calibrating methods. So the examples of these two methods are given here. Image domain method example is sense, and the case space domain method grappa. And coming to the compressed sensing method. So before that, we can see that what happens when we sample uniformly and using a variable density sampling. So coming to the uniform sampling, we have already seen that if we sample it in a uniform way by skipping some prescribed number of lines in between, for example, R is equal to 2 and a sampling factor 2, that means we are leaving out every one line in between two fully acquired lines, then we can see that the artifact introduced is similar to this. That means we have some artifacts which has some structure. The artifacts are similar to some structure appearing in this image. Whereas we acquire the signals randomly as shown here with more samples at the sampling more at the center and less towards the periphery of the case space. That is called variable density sampling. And if we acquire samples similar to this, then the artifacts introduced is more noise-like, or we can say that the artifacts are incoherent. So that is one of the requirement for compressed sensing. Why? Because here the artifacts are noise-like, it is not corresponding to any particular structure in the image. And so that is one of the important requirement for the compressed sensing principles to be applied. So that is why we prefer some random form of acquisition in compressed sensing, because it requires such an acquisition for its algorithms to work. And the most visible solution in this case is the non-Cartesian sampling trajectories. So it is a variable density sampling. That means it samples more at the center of the case space and lesser towards the periphery of the case space. So the most straightforward approximations for random sampling are in the non-Cartesian regime are radial sampling and spiral sampling, and examples are shown in the right side. So here we can see that we are sampling out of the grid, that means non-Cartesian, in a radial way or in a spiral way. So in the radial case, each of this line is called a spoke, whereas in the case of spiral, each of the only one interleave is shown here. We can have multiple interleaves as well. So each of that spiral trajectory is called an interleave. So one more advantage with this non-Cartesian trajectory is that it is less prone to artifacts like motion artifacts. For example, in the case of radial trajectory, we are acquiring each spoke, and each spoke contribute equally to the energy of the case space as opposed to the Cartesian acquisitions. So again, how to introduce some more randomness into the standard trajectories? The answer to this question is shown here. That is, we can introduce some random perturbations into the standard trajectories like spiral trajectory and radial trajectory. So again, why this randomness is more important while we are reconstructing it using methods like compressed sensing. So one more advancement in this field is the if we are given some target distribution, that means we have this variable density sampling, like we have more samples at the center of the K-space and it decreases towards the periphery of the K-space. Why don't we design such a trajectory starting from an initial trajectory? That is given in this method, that is the projection-based methods. So it initially chooses some trajectory. Again, I have shown an example here. Assume that we have been given a target density as shown in the leftmost column, and we have to design a sampling trajectory which gives samples which mimics this target density. So as an answer to this question, in this reference 8, they have shown that if we sample randomly proportional to the square of the given probability density function, then we can attain samples in a way such that the empirical distribution of this samples is more close to the given target density. So in this case, we can see that it is visually itself, we can see that if we take samples proportional to the square of the given target density, then it gives an empirical distribution proportional to the target density. Also from the PSNR values, we can see that it gives an improvement of 2 dB. This is for undersampling factor of 6. Again, the next step we have to perform in this case is that we can see that the samples are distantly separated, and so we have to interpolate these in between each of these points in order to get a continuous path, which is required by the MR hardware. It means in the acquisition we require continuous trajectories because of the gradients. That means we have to apply the gradients to acquire each of these points. So in order to apply these gradients, we need a continuous path. These points and fill in between each of these points, we need to fill some more points in order to get a continuous path. So that is done using this velocity parameterization, wherein we assume that we are traversing through the path with some constant velocity, and we fill the missing point. We fill in between these 2 points that are available using our initial trajectory selection. And what we do is like, we select all the points corresponding to the coordinates. So here we can see that we can select the points according to some particular fraction of the maximum velocity that is permissible. So based on what fraction we are taking, the number of points between the points also varies. So typically what they suggest is like use some value between 0.1 and 0.3 in order to get a physically feasible trajectory. Again, one more step we need to perform, that is this gradient. There are some gradient fields to realize the trajectory the K-space acquisition. This gradient fields have a maximum amplitude that is possible, and also it has some rate at which we can change the current. There is some limit for that. That is the slew rate constraint. So both of these constraints need to be, we do some projection onto these feasible sets that is described here. So the conventional technique, what they use is like we have an initial trajectory as shown in A, and we design the trajectory such using some optimal control approach, that is the conventional approach, wherein it follows the same support as that of A, but we can see that density of samples along the trajectory is not present. Again, the density of samples along the trajectory is well preserved in this approach. So there is some distortion associated with with this projection method, that is due to the initial curve selection as well as due to the projection distortion. So here P stands for the empirical distribution of the generated curve, whereas pi is the given target density. And W corresponds to the Wasserstein distance. And this is typically used for computing the distance between two given probability density functions. So due to the initial curve selection involved in this procedure, the final output or the final generated trajectory is always dependent on what initial trajectory we are assuming. So it always has some distortion from the target distribution. And so people thought about how to overcome this situation and how to design more efficient trajectory that can preserve the target distribution. So why don't we use this Wasserstein distance as a cost function with the constraint that the machine should satisfy some constraints. So the answer to this question is the sparkling algorithm, where they use the sparkling stands for spreading projection algorithm for rapid k-space sampling. And the objective of this method is to design k-space trajectory that are optimized, that simultaneously keeps the sampling density as well as it satisfies the physical constraints of the machine. Again, if we look at the sampling trajectory, it should preserve the variable density sampling. Also, if we look closely at any point in the trajectory or any region in the trajectory, it should be locally uniform. There should not be large gaps or clusters of samples in the trajectory. So what they use is like they solve the optimization, Wasserstein optimization, subject to the constraints, that the constraints are machine constraints like amplitude constraint and the slew rate constraint. So these are the outputs obtained using sparkling trajectory. In sparkling trajectory, we can see that they for example, if they feed a radial trajectory as the input to the sparkling algorithm, we can see that the output to the algorithm is a highly wiggled trajectory. This is a 512 by 512 radial trajectory with 34 spokes. Here also 34 spokes are there, but along each spoke they are oversampling, and as a result we obtain this highly wiggled trajectory where high density is preserved at the center and lesser towards the periphery of the k-space. So if we look at the inset of this trajectory, we can see that the points are uniformly sampled or equally spaced points are there in this trajectory. So again, this trajectory actually oversamples along each spoke, and they try with 512 samples. 512 is the input. I mean, along each line there are 512 samples. So they try with 1024 up to 3072. They increase the number of samples along each trajectory. So what they say is that even with 34 number of spokes, it will be able to cover the entire k-space region. And so in effectively, they can reduce the number of spokes from 512 to 34 in an efficient way. So similarly, they have shown the trajectory for spiral one. Here also we can see the wiggle trajectory, and with more density at the center of the k-space that decays towards the periphery of the k-space. So again, coming to the limitations of such method is that this method can be used for high readout acquisitions. Whenever the readout time is considerably short, these trajectories cannot really deviate from the simple geometric trajectories, and will not get any deviation from the simple radial trajectory. Another disadvantage with this type of approach is that the target density itself is not available in most practical cases, and it will depend upon the data set as well. An example is shown here. This is a mask. Mask means the samples to be acquired in the k-space. It does not satisfy the physical constraints, but these are simulation studies performed with deep learning based optimization of the undersampling pattern. So it is shown for knee as well as brain. So here we can see that for the brain, the trajectory is almost symmetric, whereas in the case of knee, we can say that can see that it is actually not, it is not a symmetric trajectory, and the density itself is very different from that of brain. So these considerations all are required while designing a trajectory for MR machine. So in summary, we have seen that the quality of the MR image reconstruction, particularly using compressed sensing, depends upon the sampling pattern, and the point to be noted is that we do not have an appropriate objective function for trajectory optimization, and such an objective function is still an open question. Again, the optimal sampling trajectory depends upon the region of interest or the data set we are looking for. So now let us see how we can reconstruct the image. So assume that we have a trajectory to acquire the data, and we have got the undersampled acquisitions, how to effectively reconstruct the image from this limited number of k-space samples. So as compressed sensing, in compressed sensing, we require some nonlinear reconstruction strategy to recover the efficient image, or to recover an image of good quality or clinical quality. So in compressed sensing, the objective or the optimization problem can be represented like this, where the first term in this equation corresponds to the data fidelity, where Ku corresponds to the undersampled k-space, and Fu is the undersampled Fourier operator, which is nothing but the Hadamard product of Fourier transform multiplied, with the Hadamard product of the Fourier transform with the sampling mask. Psi is the sparsifying transform operator. Omega is the sparse coefficients, and beta is the regularization parameter. So here beta controls the trade-off between the data fidelity term and the sparsity constraint. So in this problem, this optimization problem, we can solve using a simple method called iterative soft thresholding algorithm. It consists of a gradient descent update followed by the soft thresholding. The gradient descent or the Landweber update can be represented using this equation, where we take the gradients of the data fidelity term and we update the current sparse coefficient using this gradient. In soft thresholding, we soft threshold the gradient descent update using some threshold beta. Then here we have to find out what beta we have to use. Depending upon the beta, our solution will have, we may arrive at different solutions. So selecting an appropriate beta is again, we have to handle it carefully. So if we, so what are the problems associated with using a single parameter? The parameter is the beta itself. So if we use a single parameter, this method will be slow. And also how to arrive at the optimal parameter. That is a computationally demanding procedure, because we have to repeat this iterative steps a number of times and to see where this method, this parameter is optimal. Using some optimal parameter selection strategies like generalized cross validation or L-curve method or discrepancy principle, etc. In discrepancy principle, we require the noise present in the data as well, which is not really known in the case of MRI. So further, if we'll go for some methods like Monte Carlo Shure also, we have to repeat this iterative procedure for a number of selected beta values, and we have to see where this cost function for that optimal parameter selection strategy is minimum to arrive at an optimal parameter. So all these procedures require a lot of compute, use an iteration dependent parameter to overcome this solution. That is the solution that we are proposing in this approach. So if we look for an iteration dependent parameter, typically it is called a continuation method, where we start from a higher value of threshold and we decrease the threshold in each step to arrive at the optimal threshold. So previously, all continuation methods rely on the fact that we know the final beta and we are starting from a higher value of beta to arrive at the final beta. And we decrease iteration beta using some scale factor. We can use different scale factors, and each scale factor will have a different rate of decrease in the NMSE values. So here I have shown the NMSE values obtained for a reconstruction of a particular image using a given mask. And here I have shown the initial beta that we are using, and the final beta value is same in all cases, but I have changed the initial beta values. And if we change the initial beta value, we can see that with the different values of scale factor means we are taking beta 1 is equal to mu into beta 0. So if we use different in one set of realization, we are using only one mu value. And so starting from a given beta 0, what value of mu gives us the best rate of convergence in each case? We can see that this mu is equal to 0.95 when we start from an initial beta 0 of 0.10, 0.05 also 0.95 only, and 0.025 it is 0.98, and it changes with what initial beta we are taking. Also, in each case, the number of iterations required for attaining the optimal solution varies. So in each case, with the data and with what undersampling pattern we are using, all these values will vary. So how to arrive at some optimal scale factor, or how to arrive at an optimal scale factor is one question, and how to deal with this unknown final parameter. So in order to overcome this problem, we have formulated an automated regularization parameter selection strategy using continuation. Here we have introduced an additional prior into the CS MRI cost function, and we proposed an alternating minimization approach for implementation. So how we arrived at this solution, this problem formulation, or how we arrived at this extra prior function is using the fact that the at convergence, the norm of the difference between the successive iterates of the sparse solutions, as well as the norm of the difference between the gradient descent updates should be minimum at convergence. So for any intermediate step from k to k plus 1, then we can represent this using this minimization. That means it should be minimum at any intermediate step. So in any intermediate step, we know that omega hat k plus 1 depends upon the previous beta, whereas omega hat k plus 2 depends upon the present beta. So again, using triangle inequality as well as using the monotone descent behavior of this gradient descent updates, we come to this formulation. That means we minimization of this omega hat k plus 2 L2 no minus omega hat k plus 1 L2 no minus omega hat k plus 2 L2 no with respect to beta k. So here this first term is independent of beta k, and so we can represent it as minimization of minus omega hat k plus 2 as a function of beta k. So again, if we expand this, this equation by substituting what is the value for omega hat k plus 2, we can arrive at this equation, and we maximize, because it is negative of minimum. Minimization of a negative term, we can represent it as maximization problem. And if we maximize this function, we will get the optimal value for beta in this in that particular iteration. So here again, if we look at the omega hat k plus 2 function, if we plot using different values of mu k, where mu k can be represented as beta k plus 1 is equal to mu k into beta k. We have the previous beta k, and we are varying that from by substituting mu values from 0 to 1, how the omega hat k plus 2 varies. So here also we can see that it attains a peak at some point. So that maximization happens at some particular point. So what happens is, like if we take this value of mu, and we compute the beta k plus 1 using this mu 0 value, and again repeat this step, then we'll get the red curve. And using this mu 1, we can compute the next beta, and if we repeat this again, we'll get the orange, the yellow curve, and we will get mu 2 there. So if we repeat this, we can see that we'll arrive at this mu values finally converge to some particular value which is close to 1. In this case, we can see that it is slightly higher than 0.7. So the alternating minimization approach for sparse coefficients and the parameter can be represented using this equation, where j of omega beta k minus 1 is this function where we optimize for omega, and beta k we optimize using this equation. So how to solve for beta k? We know that this function exhibits a maximum, and we take the gradient of this function and equate it to 0, and we use some numerical root finding method called modified regular falsy method to find the solution for beta in this case. So these are the steps that means the iterative steps for solving beta k. The experimental results I have shown here. A1, A2, A3 shows the computing the next beta using the previous beta value. So for the first 3 iterations, so in the first iteration, initially I started with beta is equal to 1, and a small value of beta 1 into 10 power minus 4 as the other extreme. And we can see that the value converges to 0.1170 here. And this value we got in 12 iterations. So this convergence, we have fixed some tolerance for this convergence, 1e minus 4. And again, if we take this value, this final value of this first iteration for the first step for the next for computing the next beta, then we can see that it converges to some 0.0654. So again, this final value is utilized as the initial value for the next next numerical root finding. To find the beta in the next step, we see that it again converges to some smaller value, 0.0432. So we stop these iterations by looking at some tolerance value, which we fixed as 1e minus 4. And again, we can see that the number of iterations required for convergence decreases as we go from one iteration. The sub-iterations, the number of iterations in the sub-iteration stage is reduces as we go from one iteration to the next. Again, if we look at the first iteration itself, starting from different initial threshold values, then also we can see that it converges to the same value, that is almost 0.1170 as we see in the A1 of this figure. So looking at the reconstructed images, we can see that we have compared with the Monte Carlo method to the proposed method. Monte Carlo sure is taken as a gold standard method for this approach, and so it gives good reconstructions by computing the optimal parameter. So the proposed method also converges to that of the Monte Carlo sure without requiring that strenuous calculation of the optimal parameter, by automatically arriving at the required desired parameter, giving good image quality. So if we look at the empirical convergence and the reconstruction time, then we can see that the Monte Carlo sure is shown using a blue curve here, and a slight inset is shown to visualize the blue curve and the magenta curves. The magenta curve corresponds to the proposed method using different initial thresholds. So beta 0 equal to 1, 0.5 and 0.1. And we have shown if we know the final parameter and if we don't know the final parameter, what will happen. So in both cases, if we know, or if we have some beta BM, that is the benchmark parameter obtained using Monte Carlo sure, or if we don't know the parameter, then also it converges to the optimal solution. So the advantages are, we do not require such an optimal parameter selection strategy if we use this method, and also it is much faster compared to the Monte Carlo method as well, while retaining the image quality similar to that of the optimal parameter selection strategy, that is the Monte Carlo sure. So in summary, we can see that for CS MRI reconstruction, the regularization parameter always establishes some trade-off between sparsity and data fidelity. And here we have chosen the regularization parameter in each iteration as corresponding to the maximum of the L2 norm of the gradient descent update, and then the application of this method enables faster convergence to the optimal solution as well. If we start from any initial regularization parameter also, it converges to the optimal solution. So in conclusion, we can say that the quality of the MR image reconstruction depends upon the sampling pattern as well as the reconstruction algorithm. And so careful optimization of both the acquisition trajectory design or as well as the reconstruction is equally important for achieving high quality images in magnetic resonance imaging. So these are some references. I'd like to thank you, and questions.
Thanks, Dr. Raji. We'll be very happy to take questions. If there are, feel free to unmute and ask, or if you'd like to type it. Okay, while others are thinking of some questions, we have a couple of questions for you. So in slide 28, you showed us optimized masks for specific anatomies. Are they for a specific undersampling factor?
Yeah, it is for some particular undersampling factor. If I remember correctly, it is 6.
Depending on the special condition in the anatomy, depending on optimal mask will also change, right? For example, if there's a tumor, mask will also change, right? For example, if there's a tumor.
Correct, that is correct. But so far, no such studies with any specific disease or disorder have not been conducted in the literature so far.
Okay, I have one more question. So when you looked at your reconstructed images, you only looked at how far is it from the optimal reconstruction. You've not looked at numerical quality measures. Should incorporate that. You should incorporate. Correct. So
correct.
I have actually
shown the reconstructed, I mean, the NMSC values. Here I have shown, but as a table I have shown in the paper, I haven't included in the slides.
I was wondering what quality measures you use.
NMSC I have used.
Anything apart from that?
No. And in this paper I have used the visual quality difference images and NMSC. This.
You haven't used things like SSIM, structural similarity index.
No, in this paper I haven't used that. This is the reference to this paper, but we have used only NMSC. SSIM we haven't used.
Okay. So one last question from me. So what is the best possible undersampling factor you've used and yet obtained a good quality image? How far can you push? Factor of 6, 8, 10?
With conventional technique, I have seen the improvement in quality with R is equal to 6. I guess it can give good reconstructions, but with the deep learning methods and all, people have shown like we can go up to 20. I guess
20, 16, 20. That's impressive.
16, 20 they have shown in paper.
So, any questions from the audience? Looks like there are none. So, Nikhil, can we close the session?
Yeah, sure, Neelam.
Yeah, so let's thank the speaker for the nice talk. Thank you all. So see you next week for the next Samvaad-Talk. Thank you.
Thank you.